So next one is unsymmetrical aerofoil. Again, we don't take this thickness. We will take only the camber line. So this will be our final airfoil. Okay, only the camber line. And this is the general equation, fundamental equation. So here there will be a dx. There is a slope at everywhere. Okay, it is inclined. So this term also we have to take it. It is not 0. Then first step, coordinate transformation using these three equations. So substitute dx is c by 2 sin theta, x is equal to c by 2 1 minus cos theta. Either substitute and simplify. From that, again, I'm giving the solution directly. Okay, from this equation, we are finding the small gamma, then capital gamma, lift, moment, etc. and all. Again, these steps also you can refer those books. In the exam, you don't need to write it. So the complete thing is the solution. Okay, 2v. So the a naught is equal to this much. This actually you have to substitute here. Everything if you substitute, it will be a very big equation. So just to mention in the simplest way, they have taken a naught separately they are given, a n separately they are given. Okay, so this is the solution where a naught is this much, a n is this one. So actually in these derivations, I think you have to memorize this equation and this equation. If these two equations, if you memorize, remaining things and all simply substitution and simplification. Okay, both in the symmetrical and unsymmetrical aerofoil, only fundamental equation and the solution you have to memorize. So remaining things simply you have to substitute. So this clear, right? This page. So fundamental equation, coordinate transformation. This is the final equation. From that we are getting the solution, gamma. Now you can go for capital gamma, lift, etc. and all. So a naught, we have alpha and dz by dx, angle of attack and slope. And an, this we will expand. a1, a2, a3, an, up to that we can extend. Okay. So it has only the slope. So it will be a very big equation. So they simplify like this. Okay. So next step, finding this capital gamma, integral of small gamma into dx. So this is small gamma. This a naught an value at last I will substitute. Okay. So this is small gamma. This is dx. So multiply this c by 2 inside. So 1 plus cos theta sin theta divided by sin theta divided by sin theta. C by 2 everything will be cancelled. So remaining you will get integral 1 plus cos theta. Similarly here you will take integral an sin n theta sin theta. So again these are all standard solutions. So these steps also you can find it in the book. Okay, how to simplify these steps also it is mentioned in the Horton and Carpenter book. So 1 plus cos theta is pi. And here if you substitute n is equal to 1, then the solution is pi by 2. And if you substitute any other value, you will get 0. Okay, because if you substitute n is equal to 1, it will be a1 sine square. So sine square, if you integrate, you will get pi by 2. And all other n value, you will get 0. Okay. So V infinity C, a naught, this is pi. Then you have to substitute 1. That means this is a1 and this integral is pi by 2. Okay, this is capital gamma. Then substitute in this lift equation. You will get lift also. Then you can go for CL. So CL is L dash divided by half rho V squared C. So L dash you have to substitute. So cancel this common term. Remaining this is the CL. Okay. Now we are going to substitute A naught and A1. This is A naught and this is A1. Actually we had AN. So A1 means you have to substitute 1 everywhere. So A1 is equal to 2 by pi integral dz by dx cos theta d theta. So everywhere n we are substituting 1, that's it. So this is the final CL. Again they have taken the common terms. So this integral dz by dx d theta is common. So we are getting finally this CL term. Okay. So from this we found small gamma, then we found capital gamma, small gamma into dx. Once you know the capital gamma, we found lift. From the lift, we found the CL using this. Then substitute A0, A1 value. Simplify, you will get this equation. Or in the exam, if you feel simplifying is difficult, with the result, you can leave it. Okay. Okay, so now we found CL. Okay, here they found the lift slope also. dCl by d alpha. Simply this equation you have to differentiate with respect to alpha. So here there is no alpha term. So this is 0. And only here alpha is there. So dCl by d alpha is 2 pi. So for symmetrical aerofoil, we got CL is 2 pi alpha and dCl by d alpha is 2 pi per radian. Here, this is the CL equation, 2 pi alpha plus this term. Here also the slope is 2 pi. So if you compare symmetrical aerofoil and unsymmetrical aerofoil lift curve, it will be like this. Like the unsymmetrical aerofoil, the curve is little bit shifted. Okay, so this is a symmetrical aerofoil. You see, at 0 degree angle of attack, lift also 0. But unsymmetrical aerofoil, due to the camber, even at 0 degree also it will produce some lift. Okay, and this will produce 0 lift only at some negative angle. So both aerofoils, the slope is almost equal theoretically, and the unsymmetrical aerofoil curve is little bit shifted above. Is that clear? This curve. So slope is same for both curves, but for symmetrical, alpha L is equal to 0 is 0, but for unsymmetrical, alpha L is equal to 0 is some negative value, maybe minus 2 degree, like that. But here it is always 0 degree, alpha L is equal to 0 for symmetrical. Okay, so now we know both CL equations. For symmetrical, it is 2 pi alpha. For unsymmetrical, this is the equation. By comparing these two, they are writing one general equation, which can be used in the calculation and all. That is this one. CL is equal to 2 pi alpha plus alpha L is equal to 0. For example, if you apply this in the symmetrical, you know, for symmetrical, so we are getting 2 pi alpha. And for unsymmetrical aerofoil, so alpha L is equal to 0 is some negative value. So here you can substitute. That is, you can rearrange like this. Alpha plus alpha L is equal to 0. You can write it as alpha minus alpha. Because for always unsymmetrical, lift is 0 at some negative angle. So this equation is general equation, which is applicable for symmetrical and unsymmetrical. Okay, symmetrical means this is 0, unsymmetrical it will be negative. So here they are telling it is 2 pi alpha, and this term is equal to this alpha L is equal to 0. Okay, 2 pi alpha plus this is equal to the alpha L is equal to 0. In the exam, you need to write these explanations and all. So straight away, so lift, then CL equation, then you can go for the moment. Okay, this is just for your understanding. This page. Okay, so once you know the lift, you can find the moment. So same procedure. First, we are finding moment induced by the small distance. Then, if you integrate, you can get it for the complete chord line. Okay, so DL is rho V d gamma, where d gamma is gamma ds, here it is x. Sorry. So this step is already used in the symmetrical aerofoil. So again, coordinate transformation. This is x, this is dx, this is gamma. Then multiply and simplify, you'll get these terms. So 1 minus cos square is pi by 2. This term already discussed. So n, if substitute n is equal to 1, then the result is pi by 2. And this is new one, sin theta cos theta. If you substitute n is equal to 2, then you will get it is pi by 4. Okay, for other value, you will get 0. So these steps also, it is mentioned in the books. Appendix, it is mentioned, all those steps. So in the exam also, straight away you can write the solution. So A naught, this integral is pi by 2. This is A1, value is pi by 2. Here we are substituting n is equal to 2. That means A2, it is pi by 4. Is that clear? Okay. So this, from this, you are going to find Cm, coefficient of moment. So you have to divide by half rho V infinity square S into C. SC is C square because it is 2D. So substitute m dash LE and cancel that common terms. This is our final equation. Again, here also we are writing coefficient of moment in terms of CL. So for that I am taking CL equation. So if you compare, we can see this A naught, A1 and all common term. So what I'm going to do, this CL equation, I'm going to rearrange it for A naught. Then this A naught I can substitute here. Okay. So this is Cm, this is CL. So both as A naught as a common term. So rearrange this equation for A naught. Then substitute this A naught here. And substitute and simplify. This is your final Cm equation. We found CL and Cm. Now we can check center of pressure and aerodynamic center. So center of pressure, same formula. Place the force system in the XCP distance. Find the moment about the leading edge. Then convert this into coefficient of moment and lift. Then for that simplify for the XCP distance. This is same as symmetrical airfoil minus Cm by CL. And we know Cm equation in terms of CL. So here it is. That you have to substitute. Now cancel. Now this is our final XCP equation. And here you see, for the symmetrical airfoil, it is simply 1 by 4. Okay, if it is thin symmetrical or a flat plate, we got only 1 by 4. That means this value is constant. So always it is 25% of the chord. But here we have CL, A1, A2 term. Okay, let's check which are all the parameters constant. So we got CL, A1, A2. A1, A2, it will be from this term. So this time it has only the slope. Okay, there is no alpha term, only slope, and slope will not vary. Once we fix the airfoil, you will get the same slope. So A naught, A1, it will not vary if you change the angle of attack because same airfoil we are using. So A1, A2 is constant, but CL will vary if you change the angle of attack. Okay, so there it is 1 by 4 for symmetrical. For unsymmetrical, we are getting CL term. These two are constant. Pi, C by 4, everything is constant. But the CL will vary if you change the angle of attack. That's why we are going for the aerodynamic center. So for unsymmetrical airfoil, so center of pressure is not fixed. It will be moving here and there if you change the angle of attack. Is that clear? Okay, for symmetrical it is okay. For symmetrical it is fixed. For unsymmetrical it is moving if you change the angle of attack. Okay, then next point we have to check. So already I told you, first we have taken XCP, then we went for the aerodynamic center. At last nowadays we are straight away taking in the quarter guard point if you are going for the experimentation. So here also we are checking the quarter guard point, whether it is matching with the aerodynamic center or not. So I am placing the force into the quarter guard point. This is the old image. Okay, we found only the lift. So we are going to find moment about this leading edge. So lift into this distance plus this moment. Okay, so lift into distance, then this moment. It is the total moment at this leading edge point. Then find the coefficient of moment. I think these steps we discussed in the aerodynamic center derivation, the simplifications. And I am going to check moment about this quarter guard point, whether it is constant or not. So if it is not varying for different angle of attack, I can say this is the aerodynamic center. Okay. So I have taken quarter guard point as the reference point. So I am going to check whether this moment is constant or not for different angle of attack. So if it is constant, then this quarter guard point is the aerodynamic center. Okay, because the definition is moment is independent of angle of attack for the aerodynamic center. So from the moment I am finding coefficient of moment, then rearrange for moment about the quarter guard point. So we know Cm equation in terms of Cl, and this is Cl by 4. Simplify, I am getting pi by 4 A2 minus A1. So I already told you this A1, A2 are constant. It won't vary if you change the angle of attack, because A0 has only the slope value. Okay. So here he proved the moment about this quarter guard point is constant. That means the quarter guard point is the location of aerodynamic center for the unsymmetrical aerofoils, theoretically. Is that clear? Should I repeat? So first we check center of pressure. Okay. So same up to this, it is same for symmetrical aerofoil. Only the Cm will be different for symmetrical and unsymmetrical. So here we substituted Cm of unsymmetrical and simplified, we got Cl term. So Cl is alpha dependent. If alpha changes, Cl also will vary. So we found XCP is not fixed. Okay, it is varying. Then we checked the quarter guard point. Okay, particularly moment of the quarter guard point. So okay, whether it is constant for different angle, and we found there is no alpha term. It is only A1, A2 term, which is depends on only the slope. So slope aerofoil, you are not going to change it. It is constant only. So quarter guard point is the theoretical location of aerodynamic center for the unsymmetrical aerofoil.